Hello, everybody. Welcome to your free GMAT prep hour. My name is Reed Arnold. It is August 9th, 2022. Welcome to another free prep hour with Manhattan Prep. Happy to help you out. If you're looking for other free prep options, we got it for you. You can try any of our classes, online or in person, for free. The first of 9 classes, that's over 10% of the course, no charge at all. Decide if you like it, decide if you vibe with the teacher, et cetera, et cetera. I always say there's no reason not to do this. We talk about big stuff in class 1, a lot of data efficiency strategies, a lot of sentence correction strategies, and a lot of just like how the GMAT works, information. And so it's just a good thing to do for anyone starting off their GMAT journey. Totally free of charge. You can do the same thing with our Interact course. That is our video self-paced study course. We also offer Foundations of GMAT Math workshops once or twice a month for free. That is where we talk about the concepts of the GMAT test, the math concepts of the GMAT test in a very GMAT way. It's one of my favorite courses to teach. It's how I often wish I'd learned math, and I have a math degree. There are things in that course, even after getting a 760 on the GMAT and having a math minor, where it changed how I do certain processes on the GMAT and really opened up how I do certain math moves. So I think anyone can get something out of that. But certainly if you feel like you're a little rusty on those math concepts, attend one of those workshops. Really glad we started about a year ago offering that one for free. Okay, so look out for that. Today's lesson, everybody, we are talking about linear equations and the combo and expressions, but that's just another word for the combo. Okay, so we're going to talk about some algebra today, an algebra topic that the GMAT tests with some regularity. Make sure we're clear on the basics and some of the trickier things that the GMAT pulls with it. We're going to go back to high school, talk about some of those high school procedures that you need to know, but also show how the GMAT puts twists on them and lays some traps. And the fact that you can't rely purely on your high school algebra is always something I remind my students of. So we'll talk about how those traps get set. First off, the definition of a linear equation. It's an equation with variables to the power of 1. That is the definition of a linear equation. And when you graph a linear equation, you get a straight line. You get a line in the coordinate plane. Okay. A more informal definition, a more Reed definition, is that it's an equation that has a constant exchange rate between its variables. And that exchange rate we're going to come to know as the slope. Okay, if you go up 3 over 4, you're exchanging 3 y's for 4 x's, or you're gaining 3 y's every 4 x's, something like that. There is a rate ratio game that shows up in linear equations that's useful to be aware of. Okay, some examples of linear equations: y equals 4x plus 7. That is in standard form, as we'll see in a second. 4x minus 3y equals, actually, no, I said, I think actually this is officially known as standard form. This is called slope-intercept form. This is what most students are used to. But this is also a linear equation in, I think, what is known as standard form. Okay. And it's a relationship between x and y. And a y-intercept is typically what is thought of here. This equation down here, you might not look at that and see that, that doesn't look like a standard linear equation at first, but if we do a little bit of multiplication, if we know that x and y are not 0, we multiply everything by xy, the whole equation, what we're going to end up with is 3x minus 2 plus equals 5y. And that is just it's a linear equation where x and y are only raised to the power of 1. Okay. JD is asking about the exchange rate. The 7 gets in the way of being a pure ratio exercise, JD, but there's still the game where this 4 tells me if I go up 4, for every x I increase, I get 4y more. If I get 1 more x, I get 4 more y. If I have y as negative 4x plus 7, if I go 1 up in x, I lose 4y. If I go 2 up in x, I lose 8y. So there's still an exchange rate happening between x's and y's, even with the plus 7. The fact that there's a plus 7 means that it's not a pure exchange rate, right? or a pure ratio exchange rate. Although you could say it's a ratio of y minus 7 and negative 4 and x in that way. You could say the ratio of y minus 7 to x is negative 4. So there's a direct exchange rate for that. But in the standard slope-intercept form, if I get 1 more x, I either lose or gain a fixed amount for y, even with the plus 7, even if it's not a y-intercept of 0. We'll see some examples of that down the road. but that slope is a rate, it is a ratio. And so this equation down here, it still turns into a linear equation. You just have to do a little bit of manipulation to it. So this, I wrote the standard form, but I actually think, again, this is not the standard form. This is called slope-intercept form. Is when you have it in the equation y equals mx plus b, where m is the slope and b is the y-intercept. And the slope is that how much up and how much over, or how much down and how much over measurement. It's that change rate between x and y. And there is a there is a formula for slope. A lot of people memorize it: y2 minus y1 over x2 minus x1, where these are coordinates on the line, right? If I have a coordinate x1, y1, and I have a coordinate x2, y2, by the way, it doesn't matter which one is actually 2 and which one is 1. Okay, you just have to be consistent with it. You can solve for the slope with those 2 points on the line. But honestly, on the GMAT, often you can just kind of like count. I often just, up 2 over 3, the slope is 2/3. Down 4 over 5, the slope is negative 4/5. And these equations that are in standard form can be turned into slope-intercept form using standard algebra. If I add 3x to both sides, I get 4 plus 3x. Change that up and say it's 3x plus 4, because that's the same thing, and it puts it into more slope-intercept form, the way we're just saying it. Divide by 4, and I'm going to get 3/4 x plus 4 over 4 is 1. And so here's the slope-intercept form of the standard form, where 3/4 is the slope and 1 is the y-intercept. We're not going to worry too much about graphs for now. We're going to come back to the graph aspect of linear equations, but just know that that is what happened. That is why a linear equation is a linear equation, because it graphs a line. And it has a slope and a y-intercept, and that slope is the exchange rate. What we're often going to see in GMAT linear equation land is systems of equations. And the system of equations is a fancy word for more than one equation with more than one variable. It's 2 or more variables in 2 or more equations. And there's a general rule: to solve for each variable, you need to have the same number of equations. This you might remember from your high school math. If I have 2 variables, I need 2 equations to solve for them. If I have 3 variables, I need 3 equations to solve for all of them. That is the rule that the GMAT does often use, and you do need to be aware of. Right? If I just have x equals 2, y plus 5, I can't answer what x and y are. I can't solve for them. I could solve for, like, I have x in terms of y, right? This is what we call x in terms of y, because I get x equals some term, some expression, some combo, as I'm going to call them, with y in it and only y. But it's not a value for x. I can't solve for the value of x. To do that, I need a second equation. And so when you deal with 2 equations, we're going to talk about the procedures that help you solve for those 2 variables. But first, let's just take a step back for a big algebra reminder. What equals means. Equals means is identical to. Equals does not mean the answer is. Equals does not mean results in. This is something that I think lingers over from the way we're often taught math, right? We see 7 plus 3 when we're in first grade or whatever. We see 7 plus 3. We treat it as a question where the answer is 10. That's not really what's happening here. We're not saying 7 plus 3 is a question and the answer is 10. We're saying these 2 things are not different. They are the same thing. I could also say 7 plus 3 is the same thing as 2 times 5. I could say 7 plus 3 is the same thing as 4 times 10 minus 28 plus 2. I think I did that math right. I did not. 38 plus 2. That's not right either. 32 plus 2. The risks of doing math live. 40 minus 32 is 8, plus 2 is 10. These are the same thing, right? This long-looking math expression is the same thing as 7 plus 3, and it's all the same thing as 10. Equals means identical to. This is going to be the heart of all the algebra moves we're about to discuss to solve systems of equations. And this is, again, is the kind of thing that I didn't quite pick up when I was doing high school math. All procedures from algebra hinge on knowing what this equal sign means and just being logical about it. Because here's the rule. There's one rule with all equations. Do whatever you want, just don't break math. Do whatever you want, just don't break math. What do we mean by that? Well, it means if you change one side of an equation, if some number equal, right? These are two numbers that are the same number actually. So if I change the left side by some way, in order to keep this equation an equation, I have to change the right side of the equation by some way. That's what we're doing when we're doing algebra. We're really just changing two numbers that are the same number in the same way, such that we are simplifying the numbers down to a single variable on one side of the equation. And that's actually, you know, if I see something like something minus 7 equals b, a lot of times people think about like move, they'll say, you know, move the 7 over. That's not what happens. And I think it's useful to know that that's not what happens. We don't move the 7 over. We're just adding 7 to this number, and we're adding 7 to this number. The only thing that happens, or the special thing that happens, is when we add 7 to this number, the 7 vanishes. If we add 7 to this number, if there's no 7 to cancel, if there's no minus 7 to cancel out adding 7, then we just have to add 7. I can do whatever I want though. If I want, I can add 10. And then I'm gonna be left with a plus 3 on the right side and b plus 10 on the right side, right? I can do whatever. I can multiply by 2 and say 2a minus 14 is 2b. I can do whatever I want with numbers. I just can't break math, meaning I can't make the equal sign not equal anymore. And whatever I can do with a value, I can do the same thing with an equivalent value. Okay. What do I mean by that? Well, since 3 times 2 plus 4 is 10, and since 14 minus 1/2 plus 9 is 2, this is an equivalent value. If I want, I can put that where 2 was. If I can multiply 3 by 2, or I'm sorry, if I can multiply 2 by 3 and add 4, I can multiply 14 minus 1/2, I'm sorry, 14 times minus 1/2 plus 9 by 3, and then add 4. And that's, now why would I do this? I don't know. I'm not saying you would do it. I'm not saying it's a convenient thing to do. I'm just saying you can. I'm just saying if I can do it with 2, I can do it with anything that equals 2. Be it variables or numbers, it does not matter. If you can do math with 2, you can do the same math with anything that equals 2. Variables, numbers, whatever. That's the idea. So if I know that 2x plus y is 10 and 2y minus x is 5, these are linear equations that give me a value for these expressions. Anything I can do with 10 and 5, I can do with 2x plus y and 2y minus x. So I know that this product here is 10 times 5, it's 50. Now you could also FOIL it out. You could do the algebra here and say it's also 4xy minus 2x squared plus 2y squared minus xy. Yeah, you can FOIL this out too and do the algebra, but also I can just say, hey, this is 10 times 5, it's 50. I can add the two numbers. This is 10 plus 5, it's 15. Now, can I also do algebra and say 2x minus x is x and y plus 2y is 3y? Sure. I can say x, now I can say x plus 2y is 15 because that's what these two things added together is. But I also know it's 10 plus 5, it's 15. I can subtract. 10 minus 5 is 5. I can also say that's 2x minus negative x, that's 3x. Y minus 2y, that's minus y. Yeah, sure, I can do that too. And if I divide, I can say it's 10 over 5 is 2. And I don't know much, there's not much algebraic simplification on this hellish looking thing. Point is, math is math. Numbers are numbers. Whatever you can do with numbers, you can do with expressions that equal numbers, or expressions that equal expressions. Anything that is equal, you're allowed to put wherever that thing is. Wherever there's a 10, I can put 2x plus y. Wherever there's a 5, I can put 2y minus x. Okay. And we'll see where this comes into play very shortly. So let's talk about how we can use this idea to go back to high school and talk about the ways of solving systems of equations. The two major ways that you might remember are substitution and what is called combination or elimination. Some people call it different things. That's how we solve systems of equations. Okay. And they're both based on the idea of unequal sign. That is what they are based around. It's just the logic of equality. That's it. So what we do with substitution is we look to get one of the equations, and it doesn't matter which, you have as many options as you want. We look to get one of the equations with an either x equals something, so x in terms of y, or y in terms of x. Because then what we can do is take that variable, wherever that variable is, and write this thing with the other variable in it. Probably the best option here would be to isolate x, subtract 11 from both sides, add x over 4 to both sides, and multiply by 4. Whole thing, right? If I multiply this side by 4, I have to multiply this side by 4. So I get 8y minus 44 equals x. And now wherever there's an x, I'm allowed to put 8y minus 44. And so over here in this equation, I have an x. And the nice thing about doing this is now I have one variable in this equation. And so I can solve an equation that has one variable. Distribute this 3, I get 24y minus 44 times 3 is 132 plus 4y is 8. I thought I chose easier numbers than this. Maybe I didn't. 28y is 140. Well, that's not so bad. This looks kind of gross. Y is 140 over 28. Well, what we can do there is find the common factor of 7. 28 is 7 times 4. 140 is 7 times 20. So I cancel out the 7. 20 divided by 4 is going to turn into 5. So y equals 5. And then I take that, I solve for x. I plug that back in. 3x plus 4 times 5 is 20 equals 8. Subtract my 20s, negative 12. Divide by 3. X is going to be negative 4. So that is substitution. There are other, you could have substituted a different way here. I could have said, for instance, I could have said 3x equals 8 minus 4y, and then divided by 3, x minus 4y over 3. And like this is kind of sad and gross, but it does work. It is a value for x. Wherever there's an x, I can put this thing. So I could say 2y minus 8 minus 4y over 3. That whole thing divided by 4 equals 11. I have a fraction over a fraction. That's kind of annoying. Multiply by the inverse, and I'm going to say 2y minus 8 minus 4y over 12 is 11. Now here's a move I like to do when I'm solving an equation and I have fractions, one fraction, multiple fractions, whatever. You saw me do it earlier with the x and the xy in the denominator. I like to multiply by something that's going to get rid of every every denominator up front. I also see that I could actually simplify this down. Let's do that first, because I see that this 8 and 4 each have a common factor. So I could factor out the 4 here and say that that's 2 minus y. And then that 4 over 12 simplifies to something over 3. And now I can multiply everything by 3. Let's just multiply everything by 3, get rid of the denominator, I don't have to worry about it. Okay, on this side, I'd have to distribute the 3 to the 2y and then to the fraction, but that just cancels out. So I'm left with 6y minus 2 minus y. Make sure that denominator stays in parentheses. I'm subtracting the whole thing, equals 33. That's going to be 7y, add 2 to both sides, equals 35. Y is going to be 5. Same answer, plug it back in, get your x, it's going to be negative 4. So you have many different options to substitute. Okay, you want to pick the one that is easiest. Pick the one where you get the easiest variable alone, some x equals or some y equals something. So that is substitution. Solve for one variable, you plug it in. The other way of solving a system of equations is known as combination or sometimes elimination. And again, it's based on the fact that equals means equals, and you can do whatever the heck you want with numbers as long as you don't break math. The idea with combination or elimination is that you're going to change the equations if you need to. You might not need to. But what you're going to do is you're going to add the equations together or subtract the equations in some way such that something vanishes. Either the x or the y vanishes. Okay, and so what I'm noticing here is that this 4y is 2 times 2y. So let's multiply this whole equation by 2. And I get 4y minus x over 2. It's 2 times x over 4 simplifies to x over 2. That equals 22. Oops, sorry, go away, Adobe. I'm not invited to this party. Okay. And I'm allowed to multiply this number by 2 because I'm allowed to multiply 11 by 2. 11 times 2 is 22. And so this number times 2 is also 22 because this number is 11. It's just the same thing as 11. And whatever I can do with 22 and 8, I can do with these expressions with x and y. If I can add 22 and 8 or multiply 22 and 8 or divide 22 by 8, I can do that with these expressions too. Because if I can do it with numbers, I can do it with things that equal those numbers. And so what I want to do is somehow add or subtract these two equations such that that y cancels out. Doesn't matter which one you do. What I'm going to do is I'm going to do 3x plus 4y minus 4y minus x over 2. And that's going to equal 8 minus 22. And that's just because this thing is 8. And this thing is 22. And so if I subtract 8 minus 22, that's doing this thing minus this thing. These are both numbers. Usually when people do combination, they like to line it up on top of each other. And that's totally a fine way to organize this. I'm just setting up this way so you can really see what's happening logically. All we're doing is subtraction. That's all we're doing. I'm just doing it such that this y goes away. So 4y minus 4y, I'm going to have no y left. 3x minus negative x over 2, that's going to be 3.5x. That's going to equal 8 minus 22 is negative 14. If you have a sense that 3.5 is half of 7, you might go, let's just multiply by 2. Let's just say 7x is negative 28. Divide by 7, x is negative 4. And again, I can plug back in. 3 times negative 4 is negative 12. Plus 4y is 8. Add 12 to both sides. Divide by 4, y is going to be 5. Okay, again, once you solve for one, you plug in and solve together. Now, that's not the only combination you could have done. You can do whatever you want. as long as you don't break math. Keep the equations equal. And then do math with numbers, just add or subtract. I mean, you can multiply or divide, I just don't know why you would, but you can do whatever you want. Okay. If I wanted to, I can multiply this thing by 12, because that will get me a 3x. I can say 24y minus 3x equals 12 times 11. It's a little bit annoying, but it's going to be 132. And now I have 3x in both equations, so let's just add these two numbers. 24y plus 4y is 28y. The x's go away, equals 140. I did that math earlier, y is 5. Okay. That's all we do when we do these things. We're just doing math. So let's see how the GMAT might introduce a problem that has combination or substitution in it. There are other ways of doing this problem, by the way, but I want you to try it using, set up some equations with variables, with two variables, two equations, see if you can substitute and solve. I'll give you 2 minutes here. All right, that is 2 minutes. If you're at home watching the recording, feel free to hit pause and keep working if you feel confident. But also, if you don't feel confident, be used to choosing letters. So we have here a rabbit on a diet. There's two foods, X and Y. And we know the total diet that this rabbit gets. The total food the rabbit gets a day is 300 grams. So X grams of food X plus Y grams of food Y. And it helps to know exactly what my variables stand for. They don't stand for food X and food Y. They stand for a number of grams of food X and a number of grams of food Y. So those grams equal 300. Okay. Now I want to think about the protein. Food X contains 10% protein. So 10% of everything that the rabbit eats of food X becomes protein, and 15% of everything the rabbit eats of food Y becomes protein. And we're told that the rabbit gets 38 grams of protein every day. Now, there are a few different ways of doing this. What I'm going to do, I'm actually going to multiply this equation by 100. Just because I don't like decimals, fractions. You don't have to do that, I'm just going to. And then I'm going to look to either substitute or combine to get rid of one of the variables. What do I want? I want how many grams of food X. That's what the question asks for. So I might as well, if I can, get rid of food Y. And one thing I'm seeing here is like, well, if I just multiply this one by 15, 15 times 300 is going to be 4,500. I think I did this right. Let's find out. And now I can subtract. And what do I want to do? I want to subtract this one from this one, partially because this number is bigger, and also because there's more X in this one, and I want positive X if I can. It's not a big deal if you don't do it this way. But if I do 15X plus 15Y, which equals, I know, 4,500 equals this number is this number, and I subtract 10X plus 15Y, which I know is really subtracting 3,800. Well, what am I going to end up with is 5X, because 15X minus 10X is 5X, and 15Y minus 15Y is 0Y, equals 700. And so if I divide by 5, 700 divided by 5 is going to be 140. You could have also substituted. I think combination is probably a little bit easier on this one, and this once you get to this setup. I say that, maybe it's not. Probably not horribly more difficult to do substitution. Say 10X plus 15. Use a different font for substitution. If I set Y is 300 minus X, so I have 10X plus 15 times 300 minus X equals 3,800 minus X. Distribute that 15 out, that's going to be 4,500 minus 15X. It's not horrible. 10X minus 5X, I'm sorry, 10X minus 15X is going to be minus 5X. Then I subtract 4,500 from both sides, and it'll be minus 700, and that's just going to cancel out. X is 140. So you can substitute or solve. Now, there are other ways you can do here. I know someone in the chat said they use the teeter-totter method. That works. There's different videos to go over teeter-totter method. Definitely a viable option on this problem, because teeter-totter methods are about weighted averages. Weighted averages are about ratios, and many linear equations are also about ratios. It's all connected. But I'm not going to show the teeter-totter today because that's just not the purpose of this lesson. Okay, this is just a straightforward word problem where you can set up two equations and you can substitute and solve. This is, by the way, an official company GMAT problem from a practice test. So there are questions that use just straightforward high school math. But of course, the GMAT is not a high school test, not really. And while you should know all the high school math stuff we just talked about and need to brush that off, you also need to learn how the GMAT throws wrinkles into it. It makes it a little bit trickier than that. So we'll see an example of that right here. First off, a quick dust up on how data sufficiency works. For those of you that don't know, this is a very GMAT specific question. If you are not familiar with data sufficiency yet, I would highly recommend that's one of the first things you should get brushed up on, watch some videos on it, read some chapters on it, whatever you can find, understand how data sufficiency works. Here's the crash course. In data sufficiency, you're going to be asked a question and you're going to be given two pieces of information. And what you're looking for is not technically the answer of the question. You're really looking for what combination of this information, if any, is enough to answer that question. And the 5 answer choices are always the same. They're always in this order. 1 alone is enough, but 2 is not. 2 alone is enough, but 1 is not. Both taking together, if you take 1 and 2 together, it's enough, but not on their own. Or each one on its own is enough, or there's not enough. I can't answer this question. Not because it's hard, but because it's not enough information. We use a box to summarize this: 12, 10, 1, 2, T, E, N. This is what I'll show you on the next slide. I'm going to show you 5 data sufficiency questions. And I'm going to give you 5 to 6 minutes to work through them. Okay. And if you're at home, again, you can pause if you want. But I'm going to give you 5 to 6 minutes to work through these. And let's just see where we fall. Begin. So here at the 4-minute mark, I'm going to check in and just let you know that the answer to each of these questions is different. Okay. None of these 2 questions have the same answer. So if you have something that have the same answer, look at it closely, see if you're missing something. Come back in about a minute. All right, gang, that's 6 minutes. So let's talk about these. Let's talk about how the GMAT throws traps into the high school algebra world, right? Because you kind of look at these, and based on what we just talked about, right, solving systems of equations, each of these is like, well, there's 2 variables, and there's 2 equations, and I know that I can substitute or combine and solve for x, and then plug in and solve for y, whatever, yada, yada, yada. And so it kind of looks like the answer to all of these might be C, 2 variables, 2 equations each time. But actually, only the answer to the first question is C. That is the situation that, yeah, it's 2 variables, it's 2 equations. We got to solve for both of them to get the value of x. All of these other ones have a little wrinkle in them. And the GMAT loves their little wrinkles, things that they throw traps down, things that look like some high school math, but have some other considerations to take in mind. This second question, you might notice, is not asking for the value of x. It's asking for the value of x minus y. One way to know the value of x minus y is to get x and to get y and subtract. And so then, yeah, sure, I can substitute and solve, get my x, get my y, and subtract. The other way to get the value of x minus y is to find in an equation something that says x minus y is some number. Because remember, what this means is this number is the same thing as this number. It's just that this number on the left, I call x minus y. I have it in pieces with variables, but it's still the same thing as that number. We call this a combo, and it's one of the most common algebra tricks on the test. And this particular question, if we do a little bit of rearranging on this second statement, statement 1 is not enough to get x minus y. But if I do some rearranging on this second equation, I can get 2x minus 2y is minus 4. And then I can factor out that 2, or just divide both sides by 2. Let's factor it out first so it's really clear. I get 2 times x minus y is minus 4. And then when I divide by 2, I get x minus y is minus 2. And so I have my value of x minus y. Do I know x? Do I know y? Absolutely not. But that's not what the question asks for technically. And this is a big thing where our high school math differs from the GMAT, right? We almost never had to solve for combos in high school math. we had to solve for single variables. Sometimes the test asks for combos or asks you to look for combos and use combos. Be on the lookout for such a trick. When a question asks for a combo, you can almost be certain that that combo can be found on its own. Very rarely does a question ask for a combo and you actually need to solve for one and then solve for the other and you put them together in the combo. It happens, but very often, if there's a combo that is asked for, just look for that combo. And remember, x minus y itself is a number. Okay, it is one number. This is another situation where it looks like, hey, I need, this one is not a combo. This is just asking for the value of x. I have two variables, two equations. Why is the answer not C? Well, if I do a little rearranging on that second equation, 2x plus 4y is 12, I might recognize I can divide both sides by 2, and I'm going to end up with x plus 2y is 6. I actually do not have a second equation. I have the same equation twice. I just multiplied the 6 by 2, and when I multiply the 6 by 2, I also multiply x plus 2y by 2 because they're the same number. And so I don't actually have any new information. I already knew from statement 1 that x plus 2y was 6. I already knew from statement 1 that 2x plus 4y was 12, which meant I already knew that 2x is 12 minus 4y. All of statement 2 is already contained in statement 1 and vice versa. They are the same equation. And you can't substitute or combine with the same equation. It doesn't work that way. So this answer is actually E. This answer, by the way, was B, right? This statement alone is sufficient for x minus y. The fourth one here, this is just a reminder that you need to simplify as much as you can before you jump to conclusions. Get your like terms together, see what happens. This first equation on the right side, if I get my y's together, 8 minus 2 is 6, y minus negative y is plus 2y. And then if I subtract 2y from both sides, it vanishes. I'm just left with x is 6. So even though it looks like I have two variables here, I actually don't. The y cancels out, so it doesn't matter to the actual equation. So the answer to this one is A. We'll come back to this last one in a moment. I'm going to first go back and talk about the combo, because that's one of the big things I want people to take from today is understanding what they are, how they work, and to look for them. Okay, the combo is a combination of variables and maybe some numbers as well, right? 2x plus 3y, that is a combo, whose individual values are not known, but very often are not needed. There's a math term for this. We call that an expression. In Reed terms, it's just a number. It's just a value. Just like 10 is a number, and just like 7 times 2 minus 4 is a number. Yes, I can break 7 times 2 minus 4 into component numbers, 7, 2, and 4. But it's also just one number. It's 10. Because equals doesn't mean the answer is or results in. Equals means is the same thing as. I learned this last year, fairly recently. I can't remember exactly when. Time is a flat circle these days. But I learned where algebra comes from. The word algebra comes from. It comes from the Arabic meaning, and I'm going to butcher this, but al-jabar, which means the reunion of broken parts. And when I learned that definition for algebra, it kind of made my head spin a little bit, because that is just GMAT thinking to a T. The GMAT is about breaking things into pieces and then recombining them in a way that's useful to answer a question. And that's what combos kind of are. It's the reunification of broken parts, right? If I have x minus y is what, this thing, and I get x minus y is 2, well, let's just unify these things into one thing. Let's take the parts x and y, and let's just call it a number, and it's 2. Or, what I just did was 10, right? I can break that down to 7 times 2 minus 4, or I can just lump it all together and call it 10. Or just lump it all together and call it 7 times 2 minus 4. Let's just reunite it, or break it up, or reunite it. Combos are these expressions, these numbers that are in parts, but we kind of lump together and start treating like its own thing. So I'm going to give you 2 questions that utilize this concept of the combo. Obviously, keep in mind that on the test, they don't tell you ahead of time, hey, look for combos. You have to develop a habit to keep an eye out for them. Okay. So try these 2 questions. They both deal with a combo. give you 4 minutes. I'll show you how to use combos to answer them. All right, that is 4 minutes on the dot. So let's talk through these and see how the combo sneaks into these questions. Okay, this top one here, it's data sufficiency. I meant to put the 1, 2, 10. Forgive me that I did not. You were new to the data sufficiency game. We're told they each receive an hourly wage increase of 6%. So they get the same percent increase. And after that increase, we want to know how much more was Jack's wage than Mark's. And so the gut impulse is, well, I need to know what their original wages are. I need to know what Jack made. I need to know what Mark made. I'll increase Jack's by 6%. I'll increase Mark's by 6%, and I'll see how much more Jack's wage is at that point. But if I think about them independently for a second, let's break it into parts, right? I increased Jack's wage by 6%. So whatever Jack makes, let's call that J. J is Jack's wage. increase by 6%. And yes, you do need percent translation chops in this one as well. The GMAT usually crosses up topics. It's very rarely one thing being tested. There's often a few things being tested. So you need to know how to translate percents into math here. That is a 6% increase in Jack's wage. And a 6% increase in Mark's wage is similar. It's going to be 1.06 times Mark. And I want to know how much more Jack's wage is, so I subtract. This is what the question asks for. A 6% increase of Jack minus a 6% increase of Mark, let me make that clear that there's a 1 here, is how much? Because that's the difference in their wages. Well, I have the same number in front of both of those variables, so I can factor it out and see that what this is actually doing is 1.06 times J minus M equals what thing? And J minus M is just the difference in their wages now. That's Jack's wage minus Mark's wage. So if I know how much more Jack makes now, if I know J minus M, the combo, then I can answer what the new difference is just by increasing that difference by 1.06, even if I don't know their individual wages. And sure enough, statement 1 tells me Jack's wage was $5 more than Mark's. So Jack minus Mark's wage is 5. What's Jack make? What's Mark make an hour? I don't know. It could be 10 and 5. It could be 20 and 15. It could be, you know, I hope for Jack and Mark that it's something like 3,005 and 3,000. It'd be good for them. They're really high paid lawyers or something. But once that difference is $5, when we increase it by 6%, we can just increase 5 by 6%. Okay. Statement 2 gives me the ratio of their wages, but that's not going to be enough to get the difference. That tells me that Jack over Mark is 4 to 3, but J minus M could be 4 minus 3 and 1, or J minus M could be 40 minus 30, which is 10. That's not sufficient. So the answer to this question is A, statement 101. So a little rephrasing up front goes a long way, no doubt. The second question, the problem-solving question. We have a used bookstore sells paperback books for X dollars each, and hardback books for Y dollars each, and bookmarks for Z dollars each. Jeff bought 3 paperbacks and 5 hardbacks and spent 20 bucks. Let's just think about that for a second. 3 paperbacks, if each paperback is X bucks, Jeff paid 3X for the paperbacks. And then 5 hardbacks, he paid 5Y for the hardback books, and in total, he spent 20 bucks. Christine, this is Jeff. Christine bought 2 bookmarks, so that's 2Z, 9 paperbacks plus 9X, and 15 hardbacks, 15Y, and spent 65 bucks. And we want to know the cost of a bookmark. We want to know what Z is. Now, if we're in pure high school math mode, we're thinking, well, I set up 2 equations, but I have 3 variables. And how am I supposed to solve for Z when I only have 2 equations here? Am I missing an equation? Oh, you know, what do I do? How do I substitute? Well, the trick here is recognizing that this expression, 3x plus 5y, wherever I find it, is 20. This is a combo. This number is 20. Wherever there's this, I can put 20. Wherever there's 20, I can put this. They're completely interchangeable. And I want Z alone. So if I can get rid of x and y somehow, I can get Z alone. Well, I look at this thing here, and let's factor out the 3. And what I'm realizing is I get 3x plus 5y equals 65. 9x plus 15y is 3 times 3x plus 5y. And wherever there's 3x plus 5y, there's 20. So this number, 9x plus 15y, is 60. So 2z is 5. Because I subtract 60 from both sides, so z is 2.5. The answer is B. Your high school math's going to fail you here. Because you didn't do this in high school math. You always had 3 variables, 3 equations. You had to do a boatload of substitution to get everything simplified down. Look for the combo. When we need z, we need to get rid of x and y. We can say anything with this combo, we're going to be able to get, if we can, use that combo to get rid of these x's and y's, we're going to be left with z. So it can be determined, z is 2.5. Now, what is x? What is y? That I can't tell you. I don't know. I cannot solve for those. Even when I know what z is. Actually, I say that. No, I can't. Yeah, because once I know what z is, I'm left with 2 equations that have the expression 3x plus 5y. It's the same, it becomes the same expression, the same equation twice. I can simplify this one down back to 3x plus 5y equals 20, but that's not new information. So I can't solve for x and y here, or either of them alone. I can only solve for z by using a combo. So combos are very common tricks in GMAT algebra. It's something to really look out for. We are so ingrained from math to treat one variable alone at a time. And the GMAT often wants us to lump things together and just treat that lump as a number. JD, you asked, what if there is only one combo of xy for the 3x plus 5y equation? Oh, you're jumping to my next point. I didn't even think about that in this situation. So 3x plus 5y equals 20. Y could be 1, and x could be 5. That could be 2. And it could be 333 1/3, which doesn't work. You bring up an excellent point, and technically it would be a problem here because we can't have 1/3 of a penny. Hold that thought, JD. That is a good thought. You're jumping to the next point here. And technically, I think you are. This question is somewhat flawed for this reason, or it's not flawed. It's just, well, yeah. It's you could figure out what y and z are, or what x and y are. It's a very interesting point, and let's just talk about it, because that's where I was heading next anyway. Good eye. So let's look about this last question here. X and y are positive integers. What is the value of x? Again, it looks like, oh, I'm not asked for a combo. I'm asked for a variable, 2 variables, 2 equations. I need to substitute and solve. Well, the difference here is that we're told x and y are positive integers. And there are questions here that actually just tell us positive integers. Sometimes we just are in a question where we can only have positive integers. And that's actually going to change the situation here. If I have 3x plus 4y is 17, these things add to 17. Well, 4 times 4 is already 16. And that means 3x would be 1. But that would put x as 1/3. For 3x to be 1, x is 1/3. That breaks the rule because these are positive integers. So what if y is 3? Notice if y is 5, x is negative. That's not allowed. So if y is 3, I don't know why I wrote 32. If y is 3, 4 times 3 is 12. 3x would be 5, but that would make x a fraction. Again, that doesn't work. If y is 2, 4 times 8, I keep writing the answer. 4 times 2 is 8. 3x would be 9. X would be 3. So that works. I could do 3 times 3 plus 4 times 2. That works. If y is 1, 3x is 13. That's not going to work. The only integers that actually work for this statement 1 are x is 3 and y is 2. And so this is actually sufficient because of the positive integer constraint. Now, you're going to find the exact same game in statement 2. The only positive integers that work for that equation are x is 3 and y is 2. And so this is, again, where your high school math fails, where you don't usually have to do this game, but when we are told positive integers, and that's part of the information, it actually narrows down what is possible in this linear equation. Fractions are not allowed. So what JD noticed on this book question was a game similar to this. If 2x plus, 3x, because what did Jeff buy? 3 paperback and 5 hardback. If 3x plus 5y is 20, well, unless, you know, the hardbacks are $4 and the paperbacks are free, I think what's more likely is that there's one hardback bought, which would make 5 paperbacks. And that's the only, those are the only integers that actually work here. If I try to do, let's say y is 2. Let's say Jeff bought 2 hardbacks. That's $10. 3x would be 10, which means the price of a paperback would be 10/3, which is a problem because what that equals is 33.3333 cents. So you could have, the thing about this is you could have non-integer values for x. It just can't be a repeating decimal because we're dealing with cents. You can't have 1/3 of a cent, not in the real world. And the GMAT problem would be set up for the real world. I've never seen a GMAT problem actually deal with something like this. I've seen it deal with integer constraints, not hundredths constraints. But it was a sharp eye, JD. Good thing to notice here. X technically can't be a repeating decimal. And if y is anything other than 4, where x is free, which is not the story, then the only option is for y to be 1 and x to be 5. Which I'm actually realizing means that the paperbacks sell more than the hardbacks, which is usually not the case, but hey, it's a weird bookstore. So this idea of integer constraints, that was it in this kind of silly problem that I just made up, but let's actually talk about it in other situations. What you're looking for here is that exchange rate. Okay. Very often you're thinking about the exchange rate of the integers in the problem. 3x plus 4y is 17. Well, every time I add a y, every time y goes up by 1, that increases 4 to the sum. So x would need to decrease by 4, or this thing, every time this thing goes up, everything y goes up by 1, this thing goes up by 4. So this thing needs to go down by 4 to cancel out, to keep the sum the same, because the sum is fixed. But here's the thing, if x is integers, I can't go down by 4 with x being integer changes because it's multiplied by 3. I can only go in rates of 3. So what this is going to end up dealing with, I'm going to have to subtract in 12s here and add in 12s here, because that's the common multiple of 3 and 4, which means my y is going to be, and by the way, it should be plus or minus for both of these. They're just mirror images of each other. So y is going to be either plus or minus 3, and x is going to go in plus or minus 4. I'm going to trade 4 x's. I'm going to lose 4 x's and gain 3 y's. Or I'm going to gain 4 x's and lose 3 y's. Or 8 and 6, or 12 and 9, right? That's the exchange rate of the x's and y's. So you can think about how much you need to lose or gain to keep the situation fixed, to keep that sum fixed. And this happens when you have integer constraints, almost always. That's a key point here. When you have integer constraints. Think about how those x and y's trade out and make sure that you actually end up at integers. So take 4 minutes here for these two questions that deal with this integer constraint exchange rate idea. All right, Candy says about 4.5. Take a look at these. So, dealing with questions that have this exchange rate idea. Top one, we have only 10 currency bills and 25 currency bills in the pocket. But we know, so let's say 10. So the thing to note here, we don't know how many bills that Dennis has. That's part of the challenge here. But we know that in total, he has $225 units of currency. And those bills are either 10s or 25s. There's no $25 bill, but again, we're in a different land where there's $25 currency bills, 25 currency bills. The thing to set here is that, okay, well, let's call the 10 unit bills T's and the 25 unit bills F's. So 10 times the number of $10 bills plus 25 times the number of $25 bills is 225 currencies. And I don't know which of the, I want to know which of the following could be T. And notice could be means there are technically multiple possible values here. What you want to do in a situation like this is go to one extreme and use your most limiting factor, right? I can have more 10s than I can have 25s. 25 maxes out. So what is the extreme I could do here? Well, I could do 9 25s and 0 T's. And then what is the exchange rate between T and F here? If I have one less F, that's 25 less dollars I have to make up over here, but I can't make up 25 with the $10 bill. I have to do it in 50s. So I have to lose 2 here and gain 5 here, or lose 2 here and gain 5 here, or lose 2 here and gain 5 here. And this is the only number that is on that list. I can have 15 10 unit bills and 3 25s. 10 times 15 is 150, 25 times 3 is 75. Oh, I put the answer here. Darn it. Well, answer C. I was dumb. Thought I'd fixed that, but I had not. Well, let's see why the answer C. It's going to be very similar. I have 7 7s, or let's just say X 7s, plus Y 77s, where I can't have half of a 7, and I can't have half of a 77, not in this problem. Everything is either a 7 or a 77, and it equals 350. Actually, think in this one, since 7 goes perfectly into 350, we might start with X is 50. And what I'm asked for here is actually how many numbers I could have total, right? I want to know what could be the following X plus Y, the total number of numbers in the set. Well, I could have 50 X's and 0 Y's, 57s and 0 77s. That would give me 350. What is the exchange rate going to be? Well, every 77 I gain, I have to take out 77 from 7. That's minus 11. So I could have 39 7s and 1 77. Again, think about that exchange rate. That is not unrelated to slope, although I know we're not actually putting it as slope. We're not using it as slope here. It's very similar to slope. If I gain a Y, I lose 11 X's. If I gain another Y, I lose another 11 X's. But 39 and 1 is 40. So I could have 40 numbers. I could also have 30 numbers. I could also have 50 numbers. At the end of the day, I'm actually losing 10 every time I gain a 77. So when you have integer constraints, and especially if they're added together, make sure that there's actually, make sure you've actually thought about cases where X and Y are integers, and trade as needed if you need to. And don't assume if you have positive integers that you need 2 equations, if you're told positive integers. That is a big trap on this question. You assume, oh, I can't solve because it's 2 variables, 1 equation, 2 variables, I need both of them. Well, this is very limiting. If you know positive integers, either because it's a world where there's the only numbers allowed, or because it just tells you. So here, I can't have half a bill. I have full units of these bills. Here, I have full numbers of 7 or 77. Can't have half a 7 or 3/4 of a 77. I have positive integer constraints, or I guess it could be 0. Okay, cool. but I can't have a negative 77, right? I can't have a negative number in. I can't have a set that's negative numbers in the set. It doesn't make sense. So I'm constrained to positive integers. Think about what the numbers could be and think about the exchange rate between them. Last but not least, we're going to crash through this last part here, graphs, lines, and intercepts, when we actually do have to deal with the coordinate plane stuff of a linear equation. You're going to want to think about slopes and intercepts, how much up or down the line goes compared to how much over, where they cross the X or the Y axis. Those have a connection. There is a connection between slopes and intercepts that sneaks into many problems. We'll see that shortly. A few things to note: if two lines are parallel, their slopes are identical. If two lines are perpendicular, meaning they have intersected at a 90-degree angle, they have opposite reciprocal slopes. So if one slope has a slope of 3, the opposite reciprocal is 1/3. If one slope has a slope, if one line has a slope of 4, one line has a slope of 3/4, the opposite reciprocal, the perpendicular line, has a slope of -4/3. You flip the number's fraction and make it negative, and that's the perpendicular slope. We're not going to see questions with that today, but just know that that is something to look out for when you're dealing with lines in a plane. So take a look at these two data sufficiency questions. Do we know if the 90 degree is always positive? The GMAT doesn't deal with negative angle measurements. I know like trigonometry kind of does that, I think. It's a long time since I've studied trig. But yeah, 90 degrees is just 90 degrees. Or can it flip? Well, that is a 90-degree line. Oh, well, there's no 90-degree line. There's two lines that intersect at 90 degrees. So if this slope is 4, this slope is -1/4. If one of the slopes is going to be positive, one's going to be negative, unless it's undefined and 0. But you're going to have either 4, -4, or this is going to be positive 3/4, and this is going to be -4/3, or this is going to be positive 1/4, and this is going to be -4, right? But one of the slopes is going to be positive, one of them is going to be negative to intersect at 90 degrees. So take a look at these two data sufficiency questions that deal with lines in a graph. And the thing to keep in mind here is to consider slopes and intercept, and to remember we have an equation that has slope and the y-intercept in it. It does not have the x-intercept in it, but there's a way to get the x-intercept from that equation. Just a hint. So take 4 minutes to answer these, and we'll wrap up for the night. All right, it's 4 minutes. Let's take a look at these. So the GMAT, when the GMAT is asking about lines, it's asking about some situation. It's going to ask about the specifics or the relationship between slope, y-intercept, and x-intercept. And this is the relationship between slope and y-intercept. B is here. It's in the equation. It equals y minus the slope times x. When x is 0, right, the y-intercept is when x is 0. And the x-intercept is where y is 0. So we want the y-intercept of this line. We don't want anything except it's in the slope, it's in the plane, and we want the y-intercept. So we want b. No rephrasing, not much to do with that question. Statement 1 tells us the slope is 3 times the y-intercept. M is 3b. Well, I mean, you already might be able to think of like, well, the slope could be 1, or the y-intercept could be 1 and the slope could be 3, or the y-intercept could be 10 and the slope could be 30. I have no idea what the y-intercept is here. If you plug this in, if you put m as 3b, we get y equals 3bx plus b. So I guess you could factor out the b and say that that's b is 3x, b times 3x plus 1 maybe. I don't know. There's not much you can do there. Clearly different things popping up, different slopes and intercepts possible. Statement 2 gives me the x-intercept is -1/3. And you might already have a sense like, well, that's definitely not sufficient because infinite, right? If I take -1/3 for the x-intercept, here it is. There are infinite lines that go through that. I can do this line, I can do this line, that line, I can do this line. Just so many lines that go through that x-intercept. I have no idea what the y-intercept is. But here's the wrinkle on this question. While the x-intercept does not show up in this equation directly, we can solve for it because the x-intercept is when y is 0. So let's put 0 into this equation for y. That's going to equal the slope times the x-intercept plus the y-intercept. And I know the x-intercept is -1/3. So I can say 0 is m times -1/3 plus b. And if I add 1/3 m to both sides, I see that basically m over 3 is b, which tells me m is 3 times b, which is actually the exact same situation that statement 1 gave me. And so when I bring these together, I don't have new information. It actually turns out that the x-intercept gives you a relationship between the slope and the y-intercept. This kind of feels like a C. It tells me, oh, it tells me the slope is 3 times the y-intercept, and then it gives me the x-intercept, so I bet I know everything. Actually, if you know the x-intercept, you already know the ratio of the slope and the y-intercept. The y-intercept and the x-intercept are related by the slope. The x-intercept is the ratio, is the opposite of the ratio of b to m. Okay. Negative the y-intercept over the slope, that is the x-intercept. Okay. And if you know the x and the y-intercept, that ratio gives you the slope. The slopes and the intercepts are all related to each other. That's one of the key things that sneaks into questions is this interconnectedness between slopes and intercepts. You want to keep them in mind and consider possibilities and use your standard form of the equation. Okay, and at the x-intercept, that means y is 0. So the equation looks like this. So the answer to this question up here is E. And the second question here, now we want the slope of a line in the plane. Statement 1 tells me the y-intercept is 16, but again, there's infinite slopes that go through a line of 16, so that's definitely not sufficient. Statement 2 gives me the ratio of the y-intercept to the x-intercept. It's 4 to 1. And so that kind of feels insufficient too. And then you might think, oh, bring it together. Then the y-intercept is 16, the x-intercept is 4. I can get the slope from that, and I'm good to go. But actually, hold up, let's take a look at statement 2 a little bit closer. Test your cases. If the ratio of the y-intercept to the x-intercept is 4 to 1, let's actually just pull up a big paper so this is clear. I'm going to look at situations where the ratio of the y-intercept to the x-intercept is 4 to 1. So I could go to 1, 2, 3, 4, and 1. Okay, that line. That was not very good. On these points. It's close enough. Close enough right there. All right. I think I figured it out eventually. There we go. So here we go. Y-intercept is 4, x-intercept is 1. The ratio of those intercepts is 4 to 1. Well, what's the slope? We go down 4 over 1. The slope is -4. Well, what's another situation? Well, we could do 8 and 2. So up 4 more. Down, so the ratio is 4 to 1, so that'd be 8 to 2. Well, hold up, what's the slope of that line? It goes down 8 over 2. That's like going down 4 over 1 and down 4 over 1. That's also a slope of -4. And now I'm suspicious. And it turns out that actually, yeah, hold up, every line. That's just terrible. Every line that has this relationship between the x and the y-intercept is going to have a slope of -4. It's going to go down 4 over 1, down 4 over 1 until I cross the x-intercept. So yeah, the slope is also the y-intercept over the x-intercept. Or really, I guess I should say the opposite of the y-intercept over the x-intercept. The opposite of that ratio. Now you might be thinking, well, what about negative numbers? Well, okay, what if x is -1, the x-intercept -1, the ratio is 4 to 1. I know it's weird to think about negative ratios, but that would be a -4 to -1. That is a 4 to 1 ratio. Same situation. That's down 4 over 1. It's the same slope. So there's this connectivity between the slope, the intercept, the slope, the y-intercept, and the x-intercept that often creeps into questions about this. And when you deal with questions in a line, almost always you're thinking about slopes, intercepts. Yeah, slope is the opposite of the y-intercept over the x-intercept. And the x-intercept, I mean, that's a, oh, I'm sorry, I mixed up this should not, that's not the right equation. It shouldn't be B. It should be the slope, M, not B. The slope is the opposite of the y-intercept over the x-intercept. That's the same equation what I said earlier. The x-intercept is the opposite of the ratio of the y-intercept to the slope. Yeah, it's the negative part, JD. The ratio is 4 to 1, the slope is -4. Conversely, if the ratio were, and I know it's kind of weird to think about negative ratios, but it is allowed, although I don't see it on the GMAT hardly ever. I think I've seen like one question that deals with it. If the ratio of the y to the x-intercept, so let's call the y-intercept to the x-intercept, is -4 to 1, Well, I could have -1 and 4. Or I could have 4, -4 and 1. Or I could do -2 and 8. Or I could do -8 and 2. But all of those slopes have all of those lines have a slope of +4. Up 4 over 1, up 4 over 1, up 4 over 1, up 4 over 1. They're just a bunch of parallel lines that have a slope of 4. And that's because our ratio of the y to the x-intercept is opposite of -4 to 1, which is 4. So there's this weird connectivity between slopes, intercepts, and lines that are often asked about. See if you can dig in and find it. Test your cases, see what you got. So some takeaways here for linear equations. I know this, we went long, but it still was a crash course. Still, we could dig deeper into all of these. So for number 2, no, the answer here is B, JD. This gives me the ratio of the intercept, so it gives me the slope. Ratio is 4 to 1, so the slope is -4. Notice it doesn't ask for the line, it asks for the slope of the line. Okay. So I know we went long, but still, we could always dig deeper into all this. But some big takeaways. You do have to know your high school algebra here. You need to know your substitution and combination. You want to look to do it, it happens. But also look out for the GMAT tricks. Look out for the combos in particular, but look out for integer constraints as much as you can. Also simplify equations as much as you can before you make judgments. Get it down to the most simple form you can. Cancel out variables, combine your variables, get your like terms together, whatever you can, simplify it first. Okay, and when a question deals with graphs, look and think about the slope of the lines, the slopes of the lines, the intercepts of the lines, and the relation between them. In particular, keep an eye out for that x-intercept, because that's not something we talked about much in school, but it does fit into this game. It is related to the other two. All right, gang. Check out our upcoming courses at manhattanprep.com/GMAT/classes. Again, we have our free Foundations of Math courses once or twice a month. Keep an eye out for the next one of those. Try the first class of any course for free. Love to see you there. Otherwise, we'll see you at the next free GMAT prep hour. And until then, happy studying.